All right, good morning, everybody. We're going to start. I think a few more people might be trickling in, but we'll get started. So my name's Daniel Smith. I'm the Chief Technologist for Apertus Solutions, and I'm presenting on a open source project I started about a year ago called TrenchBoot, and what we're doing for measured launch for open source. And specifically, what I'm going to be covering is, going over why TrenchBoot. The relevance of dynamic launch with Zen. We'll cover some background in the security of dynamic launch itself. We'll cover the background and the goals of TrenchBoot. I'll discuss the initial capability that we have in development today, things that we're looking towards in the future, and what we want to build in Zen, and just kind of wrap up with some general discussion. So, why TrenchBoot? Launch integrity is very important to platform security. If you have your hypervisor and you can't trust that it came up in a good state, anything you try to do on top of that, you really can't rely on it. You can do VMI all you want, but if the hypervisor's been compromised, it doesn't give you anything. The addition of making sure you have the right hypervisor in place gives you the necessary security and safety features, assurances that the right security and safety features have been loaded into the system. It's all, you want that trust in your system, and if you don't have it, anything that you do on top of it, it's not there. So as a result, it's very important that we take the time and the attention to get it right and get it well integrated into the ecosystem. So dynamic launch itself is actually often underutilized. Most cases is you just use it as a step during the system launch. But the fact is that you can run a dynamic launch anytime between the power on and power off of a system. So it is actually possible to relaunch your system multiple times to reestablish the integrity of your system. We'll get into that a little bit in the further discussions. And then another thing that's really happening in the ecosystem is that hardware is actually very much evolving to incorporate launch integrity and make those core primitives in the platform. I mean, we have had the root of trust systems such as TPMs, PTT, the PSP on AMD. Secure processors are really starting to pop up. You're starting to see, the ME, the PSP like I mentioned, the T2, and the Nitro coprocessors. SPI interposers to make sure that the right firmware is getting loaded into the CPU at the power on sequence. So you've got Titan, Cerberus, and HP's SureStart. And now we're even starting to see in the ARM world these hybrid systems with the Azure Sphere MCU is very interesting because they've done this construct of an operating system, a secure world trust, and a key management framework, all providing for embedded systems. The ARM Corestone at 700 is actually building on some of these things in the die. So what is dynamic launch, and why is it important to Zen? So TrenchBoot itself was born out of the limitations that we ran into using T-Boot to launch Zen on the OpenXT project. There are several issues that we ran into. So for example, one of the big things that really started a lot of this work was the ability to forward seal the platform. In order to forward seal the platform, you need access to the TXT log to know what the measurements were, so you can use those as part of your predictions to seal the system again. There's a conflict over boot services. Who gets to terminate boot services? Who has access to it? Both T-Boot and Zen want to have access to them. So trying to deal with that and deconflict those and get it working right. T-Boot only allowed us to just measure only what multi-boot modules were loaded with it at the system boot. And then it could only give you, the only attestation it could give you is just a predetermined PCR manifest verification. So you just got a basic yes-no capability out of it. And T-Boot only supported Intel TXT. So there was no love for AMD. Some people tried to submit patches, but they were deemed to be out of scope. And so from our perspective, we wanted to support the entire ecosystem to launch Zen on all platforms in a dynamic launch capability. So the upstream Zen itself needs a good dynamic launch story that gives you a hardware-rooted integrity. You know, the ecosystem, all the competitors and these likes are, you know, building their own capabilities. You know, Google's got their shielded VMs that they're giving you this hardware-rooted integrity for your VMs. You know, Microsoft is running system guard runtime attestation. You know, that is a big thing, because if you go look at the, and it's in my notes, go look at the Octagon team and their slides that was done over the work they did. I mean, they did a very detailed look at both the SRTM and the DRTM on x86 platforms and built the capability into Microsoft Windows 10 underneath the attestation services. VMware supports it as well, and then, as I mentioned, you know, Zen does have it today with TBoot, sort of, as long as you're not trying to do it, or if you have a specific set of patches that allow you to deal with the boot services issues. So before I get into the details of it, so, is that me? I don't know what that is. Sorry, I apologize. I don't know what that was. So, to kind of get started, to have a level playing field, we want to establish some core terminology. This is, when I wrote this slide, the ARM's PSA architecture, they came out with a new firmware framework, so I did not get that to incorporate in here, so you can have a level terminology across the ARM domain. I'm not going to hit all these. The key things to consider is, you know, what a dynamic launch is, the event that's being triggered. So when I talk about DL event, that means the specific CPU instruction that starts all of this. The DCE preamble, so that's the software that's initially loaded by the DL event. And then you have the DC itself, which is what does the configuration, or I'm sorry, the preamble is what launches the instruction, and the environment is, the DCE is what does the configuration right after you come out of the event, and it sets up the DLME. So these terminologies vary across, so I'm going to use the TCG terms typically when I go through this. But if you know the technologies, this will give you a good mapping as I'm talking about these things. So when you're setting up a dynamic launch, there's a few things that you need to set up. And this is what's called the DCE preamble. You need to make sure that the system's in a very quiescent state, so that way when you do the launch, the DCE has an expectation of what the environment's going to look like, and can pick up and start executing from there. The key point, so there's Intel AMD, so Qualcomm I put in here because there's rumor that they have a DRTM coming up, so it'll be very interesting to see how they're handling this. But the key point here is that this enables you to get to a good state to begin everything. So once you've done the DL event and you've launched into the environment, this is very important because a lot of people misunderstand what's happening here. I've had to clarify this multiple times on several different with several different groups. One of the ways that I like to think about this is like the firmware stage for your dynamic launch. So what we're trying to do here is provide a very controlled and protected startup of the system. That way we know exactly how we got to this stage. There's a measurement chain that tells us what was executed by the CPU, and then this proceeds to set the bootstrap the rest of the environment up, so that way we can start to launch the DLME, and we do so that it removes the boot firmware out of the TCB, and we have a high integrity assertion of what the ME is going to have, what the DLME will have. So that is the dynamic launch itself. So what is TrenchBoot trying to do? So TrenchBoot itself is not a thing that is being created. TrenchBoot is an effort to basically do a cross-community integration across all the open source projects that might be involved with your system launch. So, you know, in the initial prototype, we've been focusing on Grub and Linux to demonstrate the capability. It's not limited to that. You know, any kernel that you want to be able to launch or use to trigger a dynamic launch, we're trying to bring this capability to all of them. So this is where we get to the areas that we're working. So right now, the initial prototype is the first launch inspection. This is your classic model of being part of the boot cycle of launching your target kernel. We actually go a little bit beyond what has been traditionally done, which we'll cover in the later slides. And then, as I was mentioning before, you can reuse dynamic launch anytime after power on. You can reuse it in particular. So this gives you an opportunity that you can actually do a runtime inspection of your system from a known good state. You can literally pause your system, relaunch, do an inspection, and then go back into your platform. The other one that I've seen people ask about is being able to handle the update or shutdown inspection, being able to inspect the system, go to a known state before you go into some execution model, such as shutting the system down and storing state to disk. You want to be in a good state, you don't want to persist anything bad, so this is a way to do that if of interest. So, who's all working on this? Right now, there's just three companies right now that are working on it. There's myself from Apertus Solutions. There's a group out of Oracle that's really focused on Intel, the Intel platform. And then there's a company out of Poland, 3M Dev, that is actually helping me with the AMD side of the house. So, the initial implementation is first launch inspection. As I said, this is your traditional being part of the boot chain as you're starting up the system. The one difference is that we're expanding this traditional approach. First, we're leveraging Linux's UEFI support to handle the handoff of EBS. So we're terminating EBS from Grub, so it's gone when we go into the DLME. So we're leveraging Linux to handle that kind of an environment. We're actually working on providing a more flexible means for measuring your environment. So there is a policy file that will get loaded along with your DLME that literally has a suite of functions that defines what suite of functions that are available in the system to measure anything from your DMI variables to disk to what you want to load next. So the options are almost limitless on what you want to do in that environment. It becomes a trade-off of how big do you want to make your DLME versus what do you want to verify before you launch into your target system. On Intel platforms, one of the things we're going to be leveraging is the S-exit instruction as soon as we're done with all of our measurements and attestations. This is one of the important things on the Intel platforms is when you do the S-exit, it protects the DRTM PCRs from being tampered with anymore until you relaunch the system. And then to launch into the target kernel, we actually are going to use the kexec system, which is actually fairly flexible. You can do a multi-boot load, you can just do a straight kexec into a Linux kernel, you could kexec into Zen specifically is what we're interested in. One capability that we'll be expanding on this is we're actually going to make the kexec interface capable of doing another late launch again. So this will give you that option to basically bootstrap again, to do a runtime attestation or something or runtime launch to reroute the system. So the implications for Zen, the things that we're going to have to wind up working with Zen on is that the kexec the kernel. We have to work. Supposedly, there's some capability in there. We just need to make sure that it will work. Is the ability to hand off the memory map through the multi-boot as we exec into the k-exec into Xen. The additional thing is that there's been a lot, talking with a lot of the Xen maintainers. A lot of them have had complaints about, the T-boot code and that it has not been maintained. So this provides an opportunity that we can now provide a strong late launch capability for Xen and enable them to reduce the code base inside of Xen itself. So to kind of help step through this is I've got a little animated slide to just kind of walk through how the startup will work once we're done. So the first thing you're going to do is you're going to see Grub load into the system. Then Grub will load either the secure loader or the ACM, depending on whether you're on an Intel or an AMD platform. Once it's loaded, that Grub will actually extend those measurements into the TPM. Grub will then load the DLME and measure it into the TPM as well. So in this case, like I said, we're using the Linux kernel as our DLME environment. So this is just a quick representation of what's in there. So there's the setup header, there is the PIGI, and then the embedded init RD, that is our what I call the security engine that executes the policy that you provide into the system to do the measurements and attestation. Once that's been loaded and recorded, Grub will then effectively function as a DCE preamble. It'll call the senter or SK-init instruction, depending on which platform you're on. Those will result in the CPU measuring those environments again. They'll get stored into the TPM as the animation kind of flow through there, and they will now have control of the system in a very controlled state, as I highlighted. All your interrupts are disabled. Memory's been depending on whether you're on AMD or Intel. So in Intel, the ACM is residing inside of RAM as cache, or cache as RAM, sorry. And the secure loader is actually in a dev, uses AMD dev to protect it from any DMA access. So once these guys have been loaded, the ACM is a little more complicated. The SL we will be writing ourselves. The SL will then basically, once it's finished measuring the DLME, it will jump into the DLME itself. Once we're inside the setup header, we start measuring all the internal pieces that we're going to be using. So the first thing we do is we take a measurement of the init RD. We then expand the PIGI, and then we actually measure the VM Linux kernel and sort all those into the TPM. At this point, the rest of the Linux startup will occur. We'll be inside the init RD, and then the init RD will take care of loading Xen, measuring it into the TPM, and then it'll do the k-exec into Xen. So that is the basic flow of the first launch scenario. Once we've finished that work, which I'll go through the timeline of that a little bit later, we get into the runtime inspection. This is actually going to be a very interesting endeavor. So we're going to basically relaunch Xen with a running Xen instance to reestablish the integrity of Xen. A key thing to think about which drives us to wanting to do this is the fact that depending on the target platform you're on, whether you're on a server, a desktop, or a laptop, it kind of changes how often you're going to be booting your system and establishing that launch integrity. So on server platforms in particular, which is one of the initial targets for this, is that they rarely get booted. So they run for a long time, so there's lots of opportunities for the hypervisor to become corrupted. So this is an opportunity during key events such as kernel upgrades or other times where we can it's acceptable to pause the system. We'll be able to either reinstall the Xen hypervisor or measure it and determine if it's in a good state before we allow the system to continue to operate. There is a few, as I said, there's a few actual use cases of interest. The server one, just a general end user might want to just occasionally check their system. For us, specifically in my role in supporting OpenXT, there are sometimes security critical events that we want to do, VMs that we want to start up. So we want to make sure that the hypervisor is in a good state before we launch those VMs. And honestly, this is an opportunity for Zen to be the first hypervisor to, at any point, to be able to securely reestablish the integrity of itself. So just to kind of step through what I was thinking of how this would work, we bring the system into a quiescent state either by pausing or sleeping the VMs. Zen will then be able to do the DCE preamble, i.e. it can initiate the late launch instruction, which will bring you into an integrity kernel. That integrity kernel could have been set up at boot time, or it could actually be set up as a special VM. We'll work through that as we start doing some of the design sessions on this. The integrity kernel will basically be able to inspect, verify, or replace the in-memory Zen instance. It will then record the measurements of everything it looked at while it was running. It can then optionally create a signed quote of everything it looked at, and then hand that back to the running instance of Zen when it exits back out. The result will be obviously a hardware-rooted runtime inspection of Zen. So if you're hunting or you need to do some security critical event and you want to be in a good environment, this will allow us to give better assurances of the environment before you do those events. So where are we at? Where we come from and where are we at? So I initially announced TrenchBoot at the PSEC conference in 2018. The presentation slide deck's up there at the PSEC site if you want to look at it. It's in the notes. In September, I gave an initial briefing to the Zen community on a Zen community call of what we were looking to do. In February of this year, we got the first working prototype on a Intel desktop system. This one's a big one, so part of the changes that we needed to make Linux able to do be the DLME for a launch, we needed to change certain aspects of the Linux kernel startup, including changing the setup header. For those that are not aware, the setup header, changes to the setup header has been this hill that a lot of people have died on. We succeeded, so there was a patch set. We did a collaboration with Peter Alvin. Based on his suggestions, we revised we did an initial patch set that will enable us to expand the setup header. That went out to the Linux kernel mailing list. The second version of it is just posted this last week, actually. It's either late last week or early this week. So hopefully that'll be going in soon. Once we have that into the kernel, we'll start bringing the rest of the kernel launch code to the mailing list to start getting all the late launch capability or DLME capability of the Linux kernel into the upstream kernel. We'll also be engaging with Zen to start working on the kexec post-EBS handoff, looking at what's currently there, seeing if it will work, see if we have to extend it. We'll be working on patch sets to come to the Zen community. Once we get past that, that's when we'll start on the runtime inspection work that I just discussed. As I said, we'll have to work on making Zen being able to do the DCE preamble, how to work the handover protocol to give the integrity kernel the information it needs for what it needs to load, what it needs to inspect, and how to jump back into Zen when it's done. So ideally, early next year, we'll start working on a formal Zen design document that we'll start sending to the mailing list and getting feedback on. So that is what we've been doing and where we're going. Start into the discussion section. So some of the problems that we want to help improve from a hardware perspective. This is my slide of opportunity for the hardware people here. AMD would really like to see an equivalent to the SK exit instruction. We want to be able to exit out of, we want to be able to lock the DRTM PCRs so they can't be tampered with. So that way we can cap them, close them, and they should not get tampered with and have to deal with those situations. STMs, so I didn't really cover it too much in this. It's not really a Zen specific item, but STM is one of the SMM handler is part of the TCB after a late launch, and we have no way of continuing to re-establish the integrity about it. STMs, introduced by Intel, provides a means to do that. There's some work going into upstream core boot that enables doing that, which is great, but we'd like to see more mainstream OEMs start adopting an STM for Intel. AMD, so we have a similar problem. There's privileged code that we can't get measurements of, so it would be good if AMD provided us either an STM or an STM-like, because I've heard discussions about whether or not SMM on AMD is really SMM. But the key point is that anywhere there's code that's loaded from firmware that we can't measure right now, we need to find a way to get that measured so we can have full integrity of our platforms. So we can try to close off any of the places where people can try to hide, where the attackers can try to hide. That leads into the device manufacturers adopting the Intel's PCI device security enhancements. Right now we have no way of knowing what the firmware is on a PCI device. Right? We can measure option ROMs. That's done by in the SRTM. But the actual firmware inside the device, we have no integrity about those devices. So Intel came up with this security enhancements that is a means by which PCI devices can do a lightweight launch integrity for their firmware, for their internal firmware, and provide that to the system to include into your measurements and attestation. So as I mentioned, we've heard rumor that Qualcomm is bringing DRTM to one of their lines of CPUs. It'd be great if ARM in general did that. You can do the static launch and establish integrity that way, but again, if we can relaunch the system on ARM as well, it gives you the same benefits that we have on x86 platforms. TPMs, right? At the end of the day, you need a root of trust for all these measurements that you're taking. TPM is by far one of the best in terms of benefit versus cost, right? It's a very cheap little chip that you can put on pretty much any board that gives you this root of trust that has fairly good strength of mechanisms about its root of trust. I mean, it's not an anti-tamper device, but it still can give you a lot. And then, of course, if ARM board manufacturers start incorporating TPMs, then you just need to get it into the boot ROMs, so that way you can have a measurement chain of ARM firmware. Reference slide. As I said, there's the Octagon, my talk, the ARM architecture firmware framework, so I would definitely recommend looking at those. So at that point, any questions? Yes?
So I saw some traffic on the mailing list for kernel. You guys linked that.
I'm sorry? We did what?
You linked the stuff in the kernel?
It has not gone in yet. So version 2 just went, so version 2 for the setup header work went, version 2 got submitted, like I said, late last week, early this week. Once it gets through and the setup header changes are in place, that way we can now extend the setup header. I didn't go into detail about that. Basically, we need the setup header, be able to modify the setup header, because when you do the late launch instruction, you need to be able to tell the preamble, i.e. grub, where the late launch entry is at, how big, the size of the kernel, everything it needs to know to set up for the preamble to set up the environment to do the late launch instruction, the DL. So once that gets upstream, then the full patch set will come right behind that. So, and we haven't published a lot of our code to we have a TrenchBoot GitHub project, but a lot of the code's been developed in a private, not private, it's open, but in a personal repository of the people that are collaborating. So, once we've kind of we're mostly there, we're just working on cleaning up the patch sets and trying to push that so that there's a clean patch set published on the TrenchBoot page, our TrenchBoot GitHub project. Yes?
So the code is on GitHub, right?
Yeah, all the code is on GitHub. It's all, both AMD and Intel code is all on GitHub. Like I said, right now we've got it in personal repositories where it's just unclean patch sets, or unclean Git commit histories. We want to clean those up to be clean patch sets to go upstream to Grub, to Linux, and eventually to Zen. So, any other questions?
What hardware will you use to play with them?
A hardware question. So, TXT is only on a limited set of platforms. Typically, it's only made available on vPro platforms, which typically are business class devices. So, a lot of your general commercial laptops and desktops will not have it. So you'll need to look for vPro if you want to use a Intel platform. AMD, luckily AMD incorporates it in all of their processors. So it's part of the secure boot capability is a core instruction inside of AMDV. So if it's a virtualized AMD chip, then you have it. So I didn't touch on this part. So from TXT standpoint, you need the ACM, which is an Intel generated piece of code. For AMD, the DCE is the secure loader. The secure loader is from AMD's part, they just left it to the implementer to write, so we're writing a secure loader, and so that's what the 3M dev guys are helping us write and get tested on AMD platforms. So, yes?
It seems with your design that there's nothing precluding you from also using SRTM. Is that a correct statement?
Correct. So from our perspective, the init-RD image, or our security engine side inside of the light launch, we're using URoot. If you're familiar with the Google URoot project for open firmware, we are codifying, measurement functions, launch functions. Right now, we're not focused too much on the attestation. The core contributors are not focused on attestation at that phase in the system. They're going to do the attestation afterwards, after they're in their main kernel, because they don't want network drivers in, because they're doing remote attestation, so they don't want network drivers in their DLME environment. But the policy file basically allows you to select which of those functions you want to execute, and it will, so the first thing it'll do is it'll execute all of the measurements. It'll then, once the measurements phase is done, it'll go through and do any attestation functions that you decided to call upon. Once it's completed that, then it'll fall into the launch action that you've chosen. Whether you've chosen just to do a plain kexec, a multi-boot kexec, or if for whatever reason you want to relaunch again into your target kernel. So yeah, the whole framework will be completely open to incorporating whatever measurements you want into the attestations. And then as I pointed out, the primary targets right now have been Grub and Linux, but we're not limited to those. We're looking at enabling iPXE to be able to do the initiate the launch. As I said, for the dynamic runtime, we need to be able to make Zen initiate the late launch, or the dynamic launch. And potentially, if there was interest, we'd be even willing to explore what it would take to make Zen the target for the launch. All right, any other questions? Yep.
Do you have any OE bits stored away to turn this on?
Any OE bits, open embedded? So right now the goal will be to publish open embedded recipes that will be able to allow you to build these. So it'll get all pushed out there. That'll be more focused on the OpenXT side of the house than the TrenchBoot side of the house. No? Any other questions? Any questions about integrity, roots of trust? I mean, I try to stay focused on Zen, but I'm very passionate about that, so I can answer any of those questions. No? All right, thank you.